Hi folks, welcome back to Physics with Captain Rod. The topic of this video is going to be thermal expansion. So what we're looking at here, just imagine a brick of material here, it doesn't really matter what it's made out of. And just for the video though, let's imagine it's kind of rectangular in shape here. So it has a length that I labeled L, a width that I labeled W, and a depth here that I labeled D. And what we're going to talk about is how the dimensions of this object will change with temperature. So imagine that we put some heat source under this maybe so that its temperature starts going up. So we're going to have an initial temperature, and imagine it goes up to some final temperature. And if we wanted to, we could calculate a change in temperature, which would be the final temperature minus the initial temperature. Now I want to talk a little bit about what's happening material-wise. So this object being solid is made of atoms, and these atoms are all bound together. And in a solid, atoms are not free to roam around. They're kind of locked in space, but they are kind of vibrating back and forth. So you can picture the solid as just, 10 to the 30th of these small particles that are locked together and just vibrating back and forth. And temperature, remember, is a measure of molecular vibration. So just to look at a quick, very simple analogy here. If I had a spring and a mass on the end of it that was free to vibrate back and forth. So this mass would be going back and forth like this. If I could somehow increase this mass's average speed, it would also increase its amplitude of vibration. So it might go back and forth maybe this far. And if I increased its speed a little bit more, the amplitude of vibration would increase a little bit more. So a similar type of thing is happening in this material. The atoms, as their temperature increases, they're vibrating back and forth, and as temperature goes up, the amplitude of their vibration goes up. So what happens is the average distance between the atoms changes ever so slightly, and boy, I mean slightly. You'd have a hard time measuring the average distance between those atoms. But cumulatively, if you add that all up, lengthwise across this entire object, what you're going to find is that this length will change a little bit. And this width will change a little bit. And this depth here will change a little bit. So what will happen is the object will actually physically get larger. So I'm going to do here is kind of model that here. So the object will actually expand some. So it'll actually be bigger. All dimensions changing. Now, one thing I'd like to point out about this expansion that I've just shown, I very deliberately made it larger so that we can see the difference, but you could not by eyeball tell this, right? Well, so if you're looking at a piece of metal and that metal warms up, you're not going to be able to physically see the difference. You'd have to, maybe put a micrometer on it. So there is an actual difference in the length and the width and the depth, but those are not things you could tell by eyeball. So the difference between the length, the difference between the new length, which I'm going to call L final here, and the old length, which I'm going to call L initial, is some change in length. Right, that would be, in this example, L final minus L initial. And I'm just going to focus on the change in length here and talk a little bit about what that depends on. Now, there's an equation that we're going to chat about here for calculating the change in length. One thing I always point out is that the equations in physics, if you spend some time and really study them, they tend to be very, very simple. Most equations in physics are either directly proportional or inversely proportional types of equations. In this example, basically, the macroscopic variable that's causing the change in length is the temperature change. So if we can imagine the temperature change here affecting the change in length, if we ask ourselves, how should the change in length depend on the change in temperature? The simplest possible function we can attach to that is a directly proportional function. So we might start with that. We might say that the change in length is equal to some constant times the change in temperature. Now, the constant here is going to depend on the original length of this object. If I have, one object that's 1 meter long and I have an identical object that's, I say identical, but I have basically the same object that's 10 meters long. I run them both through the same temperature change. The 10-meter object will change in length quite a bit more than the 1-meter object. In fact, 10 times more. So whatever this constant is for this material, it depends on the original length. There's also a material dependency, whether this object is made of brick or wood or concrete or aluminum or copper is going to be a factor. The material constant, or I'm sorry, the constant associated with the material, I'm just going to put this letter here, this is called alpha. This is called the coefficient of linear expansion. This is the material dependence of this problem. Different materials will have different coefficients of linear expansion. And this equation is how changes in length are calculated for temperature changes. We talk units on this coefficient of linear expansion. This is a very forgiving equation unit-wise. If I put the length here in meters, the change in length will be in meters. If I put the length in miles, the change in length will be in miles. If I put it in millimeters, the change in length will be in millimeters. I can actually put these lengths in any units we want. You'll notice that the units divide out in this equation. No matter what I put those units in, they're the same on both sides. So this alpha here has units of 1 over degree centigrade. Because 1 over degrees centigrade times degrees centigrade needs to be a dimensionless quantity. Now, some coefficients of expansion. I'm going to write a couple of them down and chat about them. The coefficient of linear expansion for aluminum is 24 times 10 to the minus 6 per degree centigrade. And the coefficient of linear expansion for copper is 17 times 10 to the minus 6, 1 over degrees centigrade. Again, this one is for aluminum, this one's for copper. These are values that I looked up. There's nothing special about these two. I just wanted to talk about a couple numerical examples here. 24 times 10 to the minus 6 is a very, very small number. That's what, 0.000024. And what that means is that if I take a 1 meter distance here, and I put a number of order of 10 to the minus 6 here, you need a massive temperature change to get any reasonable measurement in length. So I'm going to take a moment here and just open this up to questions before I move on to the next part. You folks listening to this have anything you want to ask yet? So this coefficient of linear expansion, this is a material dependent constant that's used when you're needing to calculate length changes in material. So in the study of thermodynamics, materials have many constants. We talked a little bit about specific heat in this class already and latent heats, and those relate heat to temperature changes or heat to phase change masses. So the coefficient of linear expansion tells us a little bit about how a material will behave when you heat it as far as its dimensions. Now, I'm going to get rid of this and talk about this thing's area. So I'm just going to kind of outline this in green. I want to talk a little bit now about this green surface area right here. That surface area has changed as well because the values for L and W have changed. If we were to try to write ourselves an equation for the change in surface area, change in area equals, it's very, very, very similar to this. We'd say to ourselves, directly proportional to the temperature change. The original area is definitely going to be a factor, so I'm going to put an A sub O here for the original area. And like all directly proportional equations, there's some sort of constant associated with the change in area here. Now, what this constant is called kind of varies book to book here. It's called the coefficient of area expansion. I'm just going to put this Greek letter beta here to represent that. So this thing's going to be coefficient of area expansion. And this is how we would calculate a change in area for any given temperature change. Now you notice that this material has two different constants already, and in fact there's a third. We can write a similar equation for volume. In fact, I'll go ahead and do that. Change in volume, running out of room though. Let me get this cleared up here. Whoops. Okay. Another equation we can write for the volume is a directly proportional equation. Change in volume is directly proportional to the change in temperature. And again, it depends on the original volume and some constant. I'm going to put, this is the Greek letter gamma here. This is called the coefficient of volume expansion. I don't feel like writing that all out. That thing's called the coefficient of volume expansion. So you notice that whatever this material is, it could have three constants associated with it. One for changes in length, which we would apply to the length, the width, and the depth. We could do that all independently. One for changes in surface area, and we can apply that to any face of this or all three faces. One for changes in volume. Now, I'm just going to focus on these two right now, the alpha and the beta, and we're just going to focus on, again, this green area here, right here. And I'm just going to write, and I need a little room to do this, so I'm going to get rid of this, and I'm just going to write out an equation here to try to calculate that change in area. Let's say that the original length is L sub O, the original width W sub O, whoops, and the original depth, I'll call that D sub O here, although I'm not going to need it for the area calculation. The new length is going to equal the old length plus the change in length, which we can write like this. The new width is going to be the old width. I want to write this a little lower. Oops. The new width is going to be the old width, which I call W sub O, plus the change in width, which we can write alpha times W sub O times delta T. The product of these two things is going to give the new volume. I'm sorry, the new area, the new surface area of that face. I'm going to go through and we're going to write this out and inspect this a little bit. So that first product is L sub O, W sub O. The outer product here is going to be times L sub O, W sub O, alpha, delta T. That's this product. And I rearranged it just slightly to put these geometric factors together. And then this product right here is going to be L sub O, W sub O times alpha, delta T. Need a little bit more room. And then the last product, when we multiply that out, whoops, is this product when we FOIL this, and that's going to be alpha squared L sub O, W sub O, delta T squared. So this product is going to represent our new area. I'll put A final here. And that's coming from taking our new length times our new width. Now, if we take a look at this thing real carefully, this thing right here, L sub O, W sub O, that represents the original area before the temperature changed. So I'm going to call that A sub O for original area. These two terms here and here are the same. L sub O, W, alpha, delta T. L sub O, W, alpha, delta T. So these can be added together to L sub O, W times 2 alpha delta T. There's a reason why I put the 2 at the alpha and I'll describe that in a second. This last term right here, you'll notice there's an alpha squared. And I put some numerical values on the board or on this sheet here before, but remember these alphas, these have order of magnitude around 10 to the minus fifth. When you take a value times 10 to the minus fifth and square it, now it's around 10 to the minus 10th. So long story short, this term is extraordinarily small compared to the other ones. So in physics, this what we do here is we do what's called a first order approximation, where we're just going to throw this term away and say that that term is approximately 0. So this quantity right here is equal to our final area. Now, this equation is saying our final area is equal to our original area plus this quantity. This quantity that I just put the squiggly under, that has to be the change in area for that green face. And I just want to compare it to this right here. So if we say that our change in area is equal to this product, which is our original area, times 2 alpha times delta t, we have an equation here that tells us the change in area. Comparing this to our original equation, you'll notice a relationship. They're almost identical. It's just that in the place of the beta, there's a 2 alpha. So long story short here, when I want to calculate a change in area, if we know a coefficient of expansion, of area expansion for a material, we can use it. But if we don't, we can use twice alpha in its place. And similarly, and I'm not going to go through the math I just don't have enough time to go through this on this video or enough space, but if I did a similar calculation for the volume, you'd get that the change in volume is equal to the original volume times 3 alpha times the temperature change. So, long story short, you can calculate changes in length using this, calculate changes in area using this, or calculate changes in volume using this. In theory, that would need 3 separate constants: the coefficient of linear expansion, coefficient of area expansion, coefficient of volume expansion, which is here. However, this guy can quite nicely be approximated as 2 alpha, and this guy can quite nicely be approximated as 3 alpha, meaning that you really only need one coefficient to calculate the 3 types of changes. So this was just meant to be an introduction into linear area and volume expansion. I think I'll just stop that video right about there. I hope this helps. Have a great day.